All right, let's go ahead and get started. So, of course, quick reminder that our test is on Wednesday. So, test Wednesday. And again, I plan on just doing it in here. So, you have time accommodations, right? That'll be honored. If anybody wants to take it in the testing center, though, just email me. Or, of course, if you're sick, just let me know as well so we can make some sort of alternate arrangements. Any questions before we get started on review? So kind of how I do these is I'll do kind of sample questions roughly from the exam, and hopefully you'll get a feel of what's on the test, and then you feel good about it. And then, of course, you can use all your notes. So let's just start with a warm-up of classifying matter. And I will post these notes, too, after I'm done. And so our options are heterogeneous, homogeneous, compound, or element. And so the ones we'll be looking at today are the following. So C60, C21, H13O2, ethanol, and Sprite. And we'll do one more of jalapeno cheese. So take a few minutes. And then, so I did get caught up on grading, at least as of over the weekend. So I know you guys are turning in more stuff. So I'll try to get these papers back to y'all. And then, of course, just double check your grade that I haven't inserted anything wrong or something didn't make it in. Jalapeno cheese. Thank you. So are we ready to go over them? So what do we get for C60? What was that? How many types of atoms are there? That's our other hint. Yeah, so there's only one, so then what is it then if it's just one element? Excellent. And so again, don't let the 60 scare you or confuse you, right? This is just an allotrope of carbon. So just kind of a reminder. So remember, those allotropes can be several of one singular atom, like we mentioned with sulfur. So S8, we mentioned phosphorus, all sorts of good stuff. What about this one? So we don't need to know what it is, but what is telling us? So C21H13O2. So compound, excellent. And we know that from our defined chemical formula here. So it's written, it's defined, so it's referring to this compound. What about ethanol? So compound, excellent. And then Sprite, so that's like the drink. What would that be? So what's in Sprite though? Yeah, so sugar, water. Yeah. And other natural flavors. And so, right, what does that tell us then? Sugar, water, carbonation, natural flavors. So it's not one thing. So what is it then? What did we say? Because it's made up of compounds. So then if it's, yeah, so then it'd be a homogeneous mixture. And then what about jalapeno cheese? And of course I picked jalapeno, right, because it's got little chunks with weird jalapeno flakes, right, and then others with not. So what kind of a, yeah, heterogeneous, excellent. Yeah, or just like uneven where you can kind of tell blobs. Well, so that's kind of the tricky part. So I did want to talk about this because with the lab, if you remember with like the sand salt mixture, so a lot of people put that like the sand salt was heterogeneous because they could be separated, but that's just because they can be separated. So like any mixture, right, can be separated. But then the question with the sand salt, and I gave it to you just because that was kind of ambiguous, but is it like uniform throughout? So is it well mixed, right, that sand salt? Or could you see like distinct like salt layers or pebbles? So maybe like the pebble salt mixture was more indicative of a heterogeneous. So for sand salt, I would put, right, could be homogeneous. So it all depends on like literally how that looked to your eye. Did it look really well mixed, or could you see, you know, big sand versus salt grains? But then like a pebble sand, that might be easier, where you can clearly see those like heterogeneous different parts of the pebbles. Does that kind of clarify those? And I'll try not to pick something like sand salt where you can argue, you know, and that's kind of ambiguous. All right, let's do the next type of problem. And so expect some converting, and there could be some different units. And so what I mean by that, sorry, my cord is getting in the way. And so I mean, it could be like the following. So convert 467 goops to floof if there are 19.5 goops in a floop. Do we have answers? And to write this one, we just had to set up our conversion factor. So I'm just formally writing what this says. So we have 19.5 goops in a floof. And of course, we could write that the other way. And then the important part was just setting up the dimensional analysis. So 467, we have goops. And then multiplying it by our conversion factor. So if we want floof, then we need to pick this one. And you could have also used a proportion. That should have also worked out. If people want me to set that up, I can. And then what do people get for their answer? 23.9. So I hear a 23.9 floofs, and then I see nods, so that looks good there. Questions on this one? And so you may also have to do some regular old metric conversions. So let's do one of those for practice. So now let's convert 7.77 times 10 to the negative 11 megameters to picometers. Do we have an answer yet? Does anybody want to put on the board for us? How we feeling? 7.77. Although the number shouldn't matter too much. You want to put it on the board? Is that a volunteering?
That was clarifying a lot.
Trying to lawyer our way out of it. All right, I'll put it up for us then. Everyone's feeling shy. And so I'll show it by two methods. So one, right, we could do our two-step conversion. So I'll write this, our what I call, right, two-step conversion, where we're looking at kind of our base units. And so what was megameter again? What did you say? So 1,000,000, so 1 times 10 to the 6, or that would be 1,000,000,000. And so, right, we can write our conversion factor. So 1 times 10 to the 6, and that's going to be meters, is equal to megameters, right, because it's multiplied times the base unit. And then our picometers, so remember those are tiny units. And so it's 1 times 10, I'll write it how your chart has it. So 1 times 10 to the negative 12 meters is equal to 1 picometer, but I like the big exponents better, so I'll put 1 times 10 to the 12 picometers is 1 meter. So these are, right, just two conversion factors. I'm going to use the ones with the positive exponents just because that's what I like. And so now let me set this up. So we'll first go from megameters to meters, again using this conversion factor, so 1 times 10 to the 6 meters on top, 1 megameter on bottom. And then if I want to go to picometers, again I'm going to use this conversion factor, could also use that one, doesn't matter, they're the same, again mathematically. And so then 1 times 10 to the 12 picometers is equal to 1 meter. So your units cancel, leaving you with picometers. So what do people get for their final answer? Any guesses out there?
7.77 times 10 to the negative 29.
I would check that again. So you could also do, right, sanity check for yourself. So negative 11 plus 12. What did you say? So not negative 7. Try one more time. Yeah, positive 7, right? You can add it up. So negative 11 plus 12 is 10 to the 1 plus 6 is 10 to the 7. So our mental math actually worked out there. Did people do it another way? So you could also set up a one-step conversion factor.
So was the 12 negative or not negative? Is that
So it depends how you write it. So how I wrote it positive, right? But you could have set it up, so let me write just like alternative. So let's say you had picked this negative 1, right? 1 times 10 to the negative 12 meters is 1 picometer. But note when you write it, so bear with me while I rewrite for a second. So, right, we do our first conversion factor. And then let's say we want to use with the negative exponents, right, because that's by your base unit. So picometers goes on top from our unit cancel. And then 1 times 10 to the negative 12 meters then goes on bottom, but that's the same thing, yeah. Since we have a negative on bottom, it's basically the same as that, so that's why it works out. We could have also done just a quick one-step conversion, and I want to at least help people kind of see that. So if this is 10 to the 6, and then picometer, right, is 10 to the negative 12, just subtract them to take the difference, right? So now 6 minus 12, so that's a 10 to the 18th difference between them. So does everybody see I just subtracted the exponents? So 6 minus 12, and then minus and negative gives you a positive. And then you know it's the little unit goes into the big unit, so you could write 1 times 10 to the 18 picometers then is equal to 1 megameter. And that would also work out. So that's how you could figure out that one-step conversion. So again, just subtract to give you that 10 to the 18 difference, and then set up your factor. So does that help people? Do we need to see it in any other ways, or? And again, you could see that this still gives you the same answer, so multiply across, so just adding to negative 11 plus 18 still gives us 10 to the 7th there. All right, let's do one more metric conversion. So now convert 5 times 10 to the 7th micrometers to kilometers. Yeah, 10 to the 7th. Yeah, so that's micro, that little mu. Do we have answers? Are we still plucking along? I'll give people maybe like another 30 seconds to a minute. And so again, I would just take the same approach so we can set up or look at our conversion factors. And so we have 1 times 10 to the 6 micrometers, right, is equal to 1 meter. So I converted it to positive exponents. So again, you could have used 1 times 10 to the negative 6 meters is equal to 1 micrometer. That would also work. And then 1 kilometer is 1,000 meters. So then we can set up our dimensional analysis. Oops. Sorry, I want my pen a little fatter. And then just setting up our units to cancel. And then, of course, from meters to kilometers. And then what do we get for an answer here?
.00 times 10 to the negative 2 kilometers.
Excellent. This is what everybody got. And so we could do mental math check. So we have 6 plus 1 times 10 to the third, so 9. So 7 minus 9 gives that 10 to the negative 2 there. And so we could also set up our one-step conversion. So kilometer is 10 to the third, right? Micro is 10 to the negative 6. So for our one step, we can again subtract. So 10 to the third minus 10 to the 6. So 3 minus a minus 6 gives us a 10 to the 9th difference. And so you get that same 10 to the 9th factor there. So we could write 1. Let me write that the positive way. So 1 times 10 to the 9th micrometers is equal to 1 kilometer. So that also works. Questions about this one? Do we feel okay on metric conversions? Okay. I'm not completely convinced, but I'm going to move on, and if people have questions, you can ask me after class as well. All right, so now let's try our periodic trends and how we might write our answers and justify them. So which has the largest radius? So phosphorus or chlorine. And then of those two, which has the higher ionization energy? So who has the largest radius and why? Any thoughts? What can we say about phosphorus and chlorine here?
Phosphorus is wider, so phosphorus.
So phosphorus has a larger radius. Good. And so I like your explanation. I just want to go a little more detailed so we're super clear. And so for a best answer, we probably want to just show the 3p, and the 3s for both phosphorus and chlorine. And so you mentioned phosphorus has 5 valence electrons, so if we fill those in, so 1, 2, 3, 4, 5, versus you said chlorine had 7. So 1, 2, 3, 4, 5, 6, 7. And then yes, so now we can clearly say, well, chlorine has more electrons on those 3p levels, so that makes its radius smaller. And so phosphorus is bigger, so good job with that. And then what does this also tell us? Since the same diagram, right, also gives us ionization information. So who has a greater ionization energy? You can use your radius answer to kind of help you. So then, which one would you have a harder time kicking off our electron? So what do we think? Yeah, chlorine. So we can use our same thought. So it has more electrons, right? It's one away. We could also use that smaller radius. So if it has a smaller radius, it's holding on just a little tighter. And so yes, chlorine has that greater ionization energy. So I'll just put closer to octet. And you could also use, again, your radius reasoning for that one. Questions on this one? And so we also covered temperature conversions. And so I would give you a temperature conversion. So let's just try one. So convert 333 degrees Fahrenheit to Celsius. And so in this case, I'll just give you the formula. And just as a heads up on the exam, the formula could be slightly different from this, so just be prepared to plug in appropriate values. And then what do we get for this answer?
Roughly 167 degrees Celsius.
So 167, is that what other people got? No, it's excellent. So just plug that in, of course. Use your parentheses. So not too difficult for that one. And so of course there'll probably be some electron configuration. So let's practice. So write, and you can use the abbreviated format, of course. So write the electron configuration and Lewis dot structure for the following. And so that's antimony, so just neutral antimony, and then sulfide with a -2 charge on it, and then tin with a +2+ charge on it. Oh, by the way, I have a homeless chapter 3 homework. Looks like it's in pen, maybe black pen. Oh, okay. What? When did you turn it in? Oh, this is older. You can check it out when class is over. Just let me know if it's yours so I can give you credit. We'll give people more time for the Lewis dot structures. Are we ready to try antimony, or do we need a little bit more time? How are we doing? All right, who wants to give us the electron configuration for antimony? So what noble gas can we start at? So krypton, and then what comes next?
5s2.
5s2. And what's after that? 4d10. And the last bit? 5p3. Nice class effort there. And then with these, so it looks like nitrogen, right? So if you look at the periodic table, it's under nitrogen, so its Lewis dot structure is just reflective of the 5s and the 5p. And so it looks something, again, like this, just like how nitrogen would look, or phosphorus, arsenic. So again, all those follow that same pattern. And again, how I drew it, like 2 in the S, and then distribute 1 in each P until we pair them. Are we ready for sulfur -2? So let's hear it. So what noble gas can we start with?
Neon.
So neon, and then what comes next? 3s2. 3p, what do people say? So I think you fell into my trap, because what's the sign on here? So it should be 3p6, right, because it has a -2. So I'll just put in parentheses, right, sulfur neutral would be neon 3s2, 3p4. But we were looking at the anion, so it had 2 extra electrons, so that's why that one was 3p6. And, oh, yes, and then it would be 3p2, yeah. And we can write that, so I'll just put other permutations. Oops, that looks like an 8, or I don't know what that looks like. Let me rewrite that. So if it was sulfur 2+, again, just to make the point, so starting with the neutral, we would have had to subtract it, so 3s2, 3p2 for the 2+ version. And so then this sulfur -2 should have the full octet. So it's best to write it showing all the electrons. And so 1, 2, 3, 4, 5, 6, 7, 8, and then put a -2 charge on it. And just for completion, right, I'll show all. So sulfur normally looks like that. So we've seen oxygen. So that's sulfur. And then sulfur 2+, again, just for completion. 2 and 1, 2 there. So just adding, subtracting electrons. And then who wants to give me 10? And so notice it's 10(2+). So what noble gas should we start with? So krypton, and then what comes next? 5s2. And what's 4d10? And then we have to stop here since it's, again, 10(2+). And so we could draw, again, reflective of 2 in the S, so something like that, with a 2+ charge on it for its Lewis dot structure. And I'm just drawing neutral 10. So neutral 10 looks kind of like silicon or germanium, so any of those. questions about these? Electron configuration, loose dot. All right, let's try another type of problem. So this problem will look really similar to one in your exam. I just go over it because it always tricks people. So it's a sheet of particle board. Is cut to a length of 6 feet and width of 3.5 feet and weighs 60 pounds. So given the density is 53.7, so that's pounds per feet cubed. So what is the thickness then of the board? And ask for it in inches. So take a few minutes, think about how you might solve it, think of what you know, density. You're given this particle board sheet, so what else can you figure out from it? And then we'll go over it. So how are we doing with this? Let's hear your thoughts. Kind of what we've set up. So what formulas might be helpful? Any ideas? Draw a little picture too. Right, you're thinking about a little particle board. So it's going to be a pretty small thickness, but then how can we calculate that, right? And we're given length and width, excuse me. So what could we do? What other formulas do we have? And how can we use density? What's that related to? So density is mass over volume. Okay. So let's just start piecing together. So we have density. And I'm just rewriting my knowns over here. And okay, well we don't have volume, but we are given mass. And then how might we find volume? So that's one way, but then what is volume just kind of like inherently? Yeah, so length times width times height. So now things are coming together. And so this is good. So now we can combine, right, these two pieces of information. So we have mass, we have density, right? We don't quite have volume. We can plug in parts of it. So we were given length and width. So I'm just going to plug this in, right? So length we said was 6. Width, oops, too many squiggles, is 3.5. So now we can start putting in all these pieces together to solve. So we said density is mass over volume. We have all our pieces for volume, or volume is mass over density. Either way, right, that doesn't matter. So let's start plugging these values in. I'll probably use this form. Again, it doesn't matter too much. So now we have 6 times 3.5 times our unknown, so our height. So right, we're still trying to find height. So that's now our value of x. So is equal to, so mass over density. So that's 60 over our density, so 53.7. And so at this point, it's just algebra once you get this set up. And so that was excellent, right? Just plugging these two in and seeing that relationship. And so people can give me numbers. And I'll punch it in as well. Oops. And then solving for heights, and then I'm just going to divide by 6 divided by 3.5. So then do you get 0.05 for the height when you solve? And of course this is in feet though. So height equals 0.0, let's see how many sig figs do we have. I try to give us 3 sig figs. So 0.0532. And that was feet. And then of course it did ask for us in inches, so we just need to multiply by 12. So 12 inches is 1 foot. And so we should get something like 0.64 or or 6/3 inches there. So questions about this one? So I would expect to see a very similar problem. We'll just have different numbers substituted in. All right, let's cover the last representative problems. And so, of course, we did some stuff with identifying, right, how many protons, neutrons, and electrons, so you might have to do that. So we have a new element, has an atomic number of 135, a mass number of 288. So how many protons, electrons, and neutrons are found in an ion with a 4+ charge? So lots of information. So we'll give people a couple of minutes and then we'll go over it. do we have answers for this one? So let's start with protons. So how many protons do we have? So 135, excellent. And so if we have 135 protons, how many neutrons do we have? So 153, so we all just took 288 minus 135, right? And then how many electrons, since it said it has a 4 plus charge? So 131. Excellent. So again, expect something crazy like that on your exam with some made up element and something like this. And then kind of the last major piece on your exam is giving formula names and naming them. And so I try to do it ambiguous the way I ask the questions. And so we'll kind of practice the format. And so the way it's worded is give the formula and name of the compound formed from the following. And so we'll say chromium 3 plus and phosphorus. Let me write out several problems. So ammonium and sulfur. Silver and phosphate. And then the last one, tungsten and oxygen. Yeah, tungsten 3 plus and oxygen on this last one. And then this one is chromium 3 plus up top. I'll squeeze one more in there, so phosphorus and sulfur, except I'm going to give you more hints. So assume 2 atoms of phosphorus and 3 of sulfur. So that's how that one would be worded, or a similar one. So take a few minutes to come up with the answers, and we'll go over them. No, so there would be 1, 2, 3, 4, 5 different problems. So then you're just trying to come up with the formula and then like the proper name for each one. Are we still working on this, or? I'll give people another minute or two to finish writing down thoughts. So let's start with this chromium 3 plus and phosphorus. So what would be the appropriate, so you can either give me the formula for it, or if you want to go ahead and name it, you can do that as well. So what do we get for this one? Anybody have a formula? Or a name, either one. So chromium, and then what do we need though between that chromium and the phosphide? Because what kind of metal is that? 3? Yep, so we need chromium 3 phosphide. So don't forget, write your Roman numerals since it's one of those transition metals. So it has multiple oxidation states. So we can put right ionic compound with variable metal, just to help you classify it, right? So we named it like an ionic compound. So we have our metal, and then of course changing the ending to "ide." And then what's our formula? So I'm going to rewrite this 3. What's our formula then? Oh, CRP, but then we don't need anything else, right? So phosphorus, and so this is kind of the scratch work for it. So chromium's 3 plus, phosphorus, right, is -3. So we can see they cancel out, and of course we can do, right, 3 and 3 for our little cross trick, but of course they cancel. So it would just be CRP there. So it looks funny, but what about ammonium and sulfur? So if someone wants to either give me the name or the formula, I'll take either one. We have Yep, so that looks great. So ammonium, you could look at your polyatomic. So you probably saw it was NH4 plus 1. And sulfur you can look, those are -2. So hence why you needed that 2 there to balance it. So that looks really good. And then how do we name it?
Ammonium sulfide.
Ammonium sulfide, excellent. So just naming our polyatomic, and then of course just changing the ending to "ide" there for our ionic compound naming. Any questions about that? And good job specifying, right, the parentheses around the whole thing, so that was a trick on your quiz, yeah.
How do we know to put the two right there? Yeah, that's
So we could, there's a couple of ways to look at it. So you can write balance of charges. I'll start writing kind of scratch work. So we have a +1 charge on the ammonium. And then sulfur, right from the periodic table, it's in group 6. So it's in -2. So we could do the swap trick. So that's kind of the easiest from the swap trick. Or you could do form, oops, I don't know why I put a 2 there. So that's one way to do it. Or you can think about the math algebraically, right? We have a +1 charge and versus a -2, so we need 2 of our +1s to cancel out that -2 charge. And you could set up the algebra. So the algebra just gives you the same thing as well, hence why the swap trick is useful. Any other questions on this ammonium sulfide one? On the swap trick or the, so with that one with the swap trick, so with the scratch work, right, I wrote 3+ above because we were given that it was a 3+ state. And then do you know that phosphorus is 3- from your periodic table? But then if you swap them, right, you get 3 and 3, which they're both divisible by 3. So you know, oh, that just simplifies to a 1-to-1 ratio there. Did that clarify or? So what about silver and phosphate? So how do we write that? How do we write the name? And we can start, so what's this phosphate if we're stuck here? So PO4, and then what's the charge on it?
-3.
So -3. So, okay, we're looking at phosphate. And then what was special about silver? Because silver is kind of one of those odd ones. What do we remember about silver? Because silver is in with our transition metals, but then we said something special about it. What are our thoughts?
Is it has a +1 charge?
Yeah, and so, right, silver always has a +1 charge. And so that's a little tricky, so you might want to star silver, right? So it's not considered one of those variable metal oxidation states. It's always considered 1+. And so let's just do our swap trick so we can all see. So this is probably the easier way to do this one. So again, silver we said is always, always, always 1+. Our phosphate, we looked at our chart, it was -3. And then we can swap them. So 1 there, 3 goes down there. And so that gives us our formula. So Ag3PO4. And then, so how would we name this then?
Is it just silver phosphate?
Yep, so it's just silver phosphate. And again, we don't need Roman numerals right on that silver because it's always 1+.
But typically, we would do metal.
Yeah, so otherwise, if it was another metal in that transition metal center, we would write it. But yeah, silver was a special one.
Even though if there's supposed to be silver, we still print it as silver.
Yeah, and so that one you might have to mark for it for
Is
your.
it only for that one, just for that one?
Yeah, so it's silver and zinc are the main ones that just have, that are in the transition metal region but have like one oxidation state. always 2 plus. So zinc's always 2 plus, silver's always 1 plus, at least, again, for our purposes here. So what about, oops, tungsten and oxygen? Trying to move this phosphorus. Oh my gosh. I was trying to create some space. So someone want to give me a formula or a name or both?
Is it W203?
So let's see, W203. So that looks promising. So let's just go through the work. So tungsten is 3 plus, so I just put the 3 plus there. Oxygen is always -2. And so, yes, I agree with your answer. That looks great. So, right, swap trick gives us that W203. And then how do we name it? So tungsten. So look at where tungsten is, though. Yeah, so then we got to use the Roman numerals. So what's the Roman numeral? 3. So tungsten 3, and then what's the last part? Oxide. Good job. Questions on this one here? And then what about the last one? So it says it's phosphorus and sulfur, but I had to give you, because again, there's so many combinations, it's 2 atoms of phosphorus, 3 of sulfur. So what's our proper naming? How do we write the formula? So P2S3, and then how do we name this? What type of compound is it? Yeah, so covalent compounds, so then how do we name it? So what do we do with the covalent compounds? What do we have to use? What did you say? Yeah, di. So diphosphorus. And I hear a trisulfide. Excellent. So with those covalent ones, that's where we use all those prefixes. All right. So let's go over some other stuff. So I forgot there's another tricky one with some algebra. But again, we'll go over it really quickly. So gallium has 2 isotopes. And so I'll give you that the average atomic mass is 69.723 AMU. And the 2 isotopes are gallium-69, which has a mass of 68.9255 AMU, and gallium-71, which has a mass of 70.9247 AMU. And so given this, what is the percent abundance of each? So see if you can try to figure it out, but otherwise we'll go over the trick so you'll be ready for your exam. So I'll give out the trick if you're kind of struggling. And so if you recall, right, the whole average, so this is kind of from our notes, but the average, right, was equal to the sum of, we said, right, the isotope 1 times the percent abundance as a decimal. And then we added all those up. So in this case, there's 2 of them. So then we can say, well, the abundance of X, which it doesn't matter which one we assign X, but let's just call this one X for explanation's sake. So gallium-69 is X, gallium-71 is Y. So we're saying, well, X plus Y has to equal 100%, right, abundance. And so then we can say, well, Y is equal to 100 minus X. And so now we have enough information to solve and plug in for our variables. And so I'll set up the algebra and then I'll give people a little more time to plug it in. But then this gives us, so if our average is 69.723, so 69.723 is equal to, so then our abundance, or our mass, excuse me, of isotope 1, so 68.9255 times X, plus our second isotope, so 70.9247, and right, this would be Y, but then we have to substitute it in terms of X, right, so we don't have too many variables, and then it's just 100 minus X for that last one. So does that at least kind of make sense for the setup of this? And again, you're seeing it now so that you won't be scared on the exam. And then, so now try that out with the algebra. So you have to distribute, right, the 70s, so 70 times 100, and then 70 times a negative X. So I'll give people a few minutes to punch through the algebra, and then we'll go over the answer. Trying to show everything. And zoom in if you need as well. Oops. I screwed up. This should have been 1 minus x. I'm so sorry. I led y'all astray. Sorry, so this should have been 1 minus x. I was like, this isn't working. Since it's a decimal, I apologize. All right, one more time. So again, I apologize for plugging that in wrong. So again, it should have been 1 since it's multiplied by the decimals. So even though they equal 100%, we have to convert it to the decimal when doing the algebra here. So I apologize again for putting that in wrong. And then once you do the algebra, did you guys get x is 60.3? And that would be if you set the gallium 69, so this would be a 60.3% abundance, and then leaving this one at about a 40% roughly. And I can go over that again or show the algebra. So again, just distribute minus x, so I just subtracted 69 minus 70, and then, okay. So starting from here, so right, we have 68.9255x plus 70.9247 minus 70.9247x. So then we're here, so then I'm just going to subtract. It doesn't matter who we do what. So I'll do minus 70 on both sides. Is 70.247. And 69.723 minus that, so 70.9247. So you get like negative 1.2. 017 is equal to, so then adding the x's together, so 68.92x minus 70. So then we get negative 1.992x. And then divide to solve for x.
It had 3 9s. Does that matter?
Oh, 99, my bad. So then just divide, so negative 1.2017 divided by negative 1.9992. And that's how we get the 60% for x, or so x equals 60. And you could round to like 60% roughly. Does that clarify this problem? And then, so the last thing, so we're not going to go over any Lewis dot structures, but we're just going to talk about what, right, we need for success. So of course we want the total number of electrons to be correct. So just want to show that work, right? All your valence electrons accounting for charges. So valence electrons plus charges, and then just drawing that out, making sure that your structure reflects that. And so your structure should show the correct total number of electrons. And then of course don't forget about your geometries, so just those basic ones that we talked about. And then you might have to identify, some sort of polar versus nonpolar, so looking for that symmetry or no symmetry. And then, of course, don't forget formal charges as well in there. But I think that's mainly it. And then, of course, if you have questions, I'm here. I have my office hours after this. And then I will post lecture notes as a PDF so you can follow along. And then I'm going to stop the stream.